Hello and welcome to my dissertation defense talk, Supporting Word Learning with Language Internal Distributional Statistics, a place for the recurrent neural network. Let's talk about where we're going today. First, I will introduce lexical semantic development, the problem of learning in the absence of extralinguistic perceptual input. I'm going to talk about a procedure that can deal with this problem, the distributional extension of category-associated features. And then, given that I'm interested in modeling this procedure, I will talk about some theoretical considerations, such as lexical atomicity, which will be explained in quite some detail. I'm going to talk about some results from modeling, simulations, computational work that answer questions such as, well, when does lexical atomicity emerge in neural language models? And how can we promote it in neural language models? And in particular, how can we do so with staged learning? And lastly, I will make some concluding remarks. So to begin, let's talk about word learning, or in other words, lexical semantic development. This is a well-known problem in psychology where children are supposed to learn how to map sound categories, for example, words like gorilla, to semantic features. They can be propositional or experiential, whatever your favorite theory of semantic properties and meaning is. Essentially, children are faced with having to map words onto these semantic features. And we call this the word referent mapping problem in language acquisition. Now, how do children achieve this word referent mapping? They use quite a number of different cues, strategies, and biases. Occasionally, parents might label objects directly. This is called ostensive labeling, and this is probably the most direct way of learning word referent mappings. But this doesn't happen a lot. Parents aren't teachers. Children use much more sophisticated tools like keeping track of co-occurrence statistics, like between words and reference across many situations. So they will try to keep track of which words they heard in the presence of which objects, and then try to infer after doing some statistics over a number of trials, which word is most likely to refer to which object. Now, all of this is, of course, helped by things like social cues, joint attention. Children won't just pay attention to anything or consider any potential word referent mapping hypotheses. They'll be sensitive to where parents look, eye gaze, gesture, all these sorts of things, including social communicative pressures. So children know that speakers have intentions, that they have shared experiences, in some cases, that, you know, what speakers tend to want to talk about are things that are relevant to the speaker or the child, and that, of course, tames the word referent mapping problem quite a bit. All of these things are important and have been studied, but usually require the presence of reference, right? But what do you do when referential information is poor or reference are simply not present? What do you do then, right? How do you then learn the meanings of words if you can't map words onto any objects in the environment? Well, there's a number of things that you could do. For sure, leverage experiential knowledge, right? If I say, woke up this morning, went to the kitchen and fried some glimpse. You know, you have some knowledge about how the world works, what things tend to be fried in the morning, presumably breakfast foods, presumably eggs, sausages, right? But, you know, put yourself into the mind of a young language learner. They might not have this kind of rich experiential knowledge. And what can they do instead or in addition? Well, this is topic of this talk, it's fairly likely that they leverage language internal distributional knowledge. So knowledge about how words pattern statistically with one another in the language that children hear. Let's illustrate this. Imagine you hear the sentence, "The gorilla eats bamboo." Don't know what gorilla means. There's no gorilla present, right? What do? It's not really a mapping problem so much anymore, as it is a kind of leveraging previous knowledge problem. So if you were to leverage distributional information, right, language internal statistical information, you could infer semantic category membership of gorilla, right? You couldn't infer exactly what gorilla meant, but you can get into an approximate ballpark meaning for that word. So you might infer semantic category as follows. Retrieve distributionally similar words. So you might have seen the words bird and cat occur in similar linguistic contexts, right? The bird eats worms, the cat eats mice and things of that sort. Very similar to the gorilla eats bamboo. And then having retrieved those words, you can isolate shared semantic features, right? So bird and cat are both animals, they're both animate words. So now you've extracted and isolated, right, semantic features, which now you can potentially extend to the word gorilla. So you can induce a novel representation for the word gorilla and populate it with those semantic features. And this is done entirely using distributional knowledge, of course, while interfacing with semantic properties. I call this procedure DCAF, the distributionally mediated extension of category associated features. Why? Because, well, the procedure for doing this is guided or mediated by distributional knowledge. Ultimately, this procedure is an extension of meaning, and in particular, an extension of category associated features, right? So features associated with the semantic category of gorilla, rather than features about gorilla. There's some fantastic preliminary work showing that children actually do this, right? This is actually really hard to do, and that's why there's only a couple of studies of this type. Some fantastic studies were done by Laney and Safran and others around 2010, 2008, 2011, where they combined artificial grammar learning in children, and on top of that show that the knowledge that children have learned during exposure to distributional cues in the artificial language, as well as phonological cues, right, help children perform word referent mappings, and more importantly, help children infer category membership of novel words they have never heard before, right? As long as they occurred in distributionally diagnostic contexts, children were able to use that information to infer semantic category properties of the novel words. So this is something that most likely does occur in children. There hasn't been any sort of computational work examining what potential cognitive mechanisms might be at play. And this is precisely where this thesis comes in and tries to make some progress. All of this is actually very related to the distributional hypothesis, right? Well known in psychology. And the distributional hypothesis claims that people learn word meanings in part by knowing how words pattern with other words in the speech they hear. And this is a wonderfully productive, successful theory in psychology. I just want to make a brief comment about how my work differs from the sort of standard distributional hypothesis. So the role of language internal distributional information, right? It's not just a direct source of knowledge about word meaning, as is supposed by proponents of distributional hypothesis, right? What I argue and others like Laney and Safran have argued is that it's additionally a tool that can potentially help children learn semantic properties of novel words, right? So these are actually very different applications of the distributional statistics in language. One, to directly help construct meaning, right, where you use distribution information directly and incorporate it into some semantic memory or lexicon. But what I'm going to be doing is to just use it as it is, not to move it into some semantic lexicon, but to use it to extend what's already in the semantic memory, right? To help learn novel words. And distributional hypothesis is relevant for another reason, one being that wonderful, fantastic models have been proposed in the past that are computationally instantiate this idea. A bunch of them have been based on the idea of co-occurrence counting, right? You count how many times a particular word co-occurs with another word in some language sample and keep track of it in a big co-occurrence matrix. They can go pretty large. There is another class of models that I argue is, while not traditionally considered to be distributionally semantic, models, they can be used as such. And these are the neural language models, like recurrent neural networks. All of these models do what's called next word prediction or language modeling. So the reason that I've chosen this class of models, right? So in other words, the recurrent neural network language model is because they do a lot more stuff than just co-occurrence counting. And I think do it in a way that is a bit more cognitively plausible, that makes a bit more contact with developmental constraints, memory constraints, right, of human brains, and in particular children. There's quite a bit more that I could say here. So RNNs have a much broader coverage of empirical findings in the psychological literature, right? Not only are they able to account for many phenomena in sequence learning, they also explain, human behavioral data when it comes to processing recursive sentences or sequences with embedding clauses and so on. Basic grammatical phenomena, number agreements. They make a contact with ideas known as predictive processing, predictive coding, which makes contact with ideas in neuroscience. There's link to neural dynamics, and when we're using the recurrent neural network, what we're doing is we're working at the algorithmic level. So as opposed to the computational level, right? In Mars, 3 levels of analysis. And that doesn't make the RNN inherently better than other models that operate on the computational level. But I prefer working at that level of analysis because it sort of places additional constraints on model development and building. And I find that to be useful in my work. Okay, so we've motivated a model. We have situated ourselves. We know what kind of task we're trying to model. Let's further defend my model choice. So in general, distributional semantic models, right, can account for tons of behavioral data in language processing. So for example, semantic priming, association norms, lexical decision, and more recently, and especially neural network language models have been shown to account for variation in human neural activation data. So for example, fMRI recordings during participants performing various semantic tasks. So all of this is to say that distributional semantic modeling is quite fruitful, and in particular, the choice of model is really important, and the recurrent neural network in particular seems to be very promising, as well as other neural network language models. There's, of course, criticisms with any great theory in psychology. One being Harnard's symbol grounding problem. The idea is straightforward, that if you're just tracking distributional statistics between word forms, you're not really tracking anything about what these words actually mean. So what is their content, right? How do they connect, link up to the real world? How do they link up to experiences, perceptual stimuli, and so on and so forth? And people like to say that if you're just tracking co-occurrence patterns in language, of course you can't account for all aspects of real-world semantics, and I think that everybody would agree with that. I just want to say something about this. Criticism actually doesn't really apply here as much as it does in other work on the distributional hypothesis. Remember, because I'm interested in how distributional statistics can be used to extend, right, rather than to construct meaning. So the language statistics that I will use to train the recurrent neural network, I will not consider that to be knowledge proper of meaning of words, but simply statistical knowledge that can be useful in helping extend existing meanings, right, that the child already has available. So let's take a look at the task in a bit more detail, right? So the procedure that I've termed distributionally mediated extension of category associated features looks as follows. Imagine you've heard a bunch of sentences. We're going to use English here as an example. And you hear another sentence, you don't know the word gorilla, right? And the problem is you want to know what that means without, relying on the presence of gorilla in the room, right? Imagine there is no gorilla in the room. That is, there is no reference to which you can map that word onto. What do? Well, again, if you're going to leverage distributional semantic information, you might notice that all of these words that I've highlighted in blue share distributional syntactic properties with one another, and you can figure that out, access memory of stored distributional knowledge, retrieve words that have occurred in similar contexts like bird and cat, right? All of these are subject of the verb eats. And what you can then do is isolate shared semantic features and then extend those to gorilla, and voila, you now have a ballpark idea of the meaning of gorilla. In particular, you know that it is an animal, that it is animate, and so on. Now, what else do we know about this procedure, right? This isn't just, you can't just extend features from any word to any other word. This type of extension must be constrained by word order, as others have shown before. Let's illustrate this idea. So, for example, if you didn't know the word bamboo, and you would be incorrect, right, to assume that just because bamboo also co-occurs with eats, that the words bird and cat here would be relevant. No, the failure here is to keep track of the order, right? In particular, bamboo occurs after the verb eats and not before, right? In every other way, co-occurrence statistics are the same, right? If you're just keeping track of how many times the word has occurred with what other word, like bamboo and eats, and if you're not tracking the order, right? So does it come before or after, right? You're not going to produce useful knowledge, right, for performing decaf, right? So if you didn't track word order, you'd make incorrect inferences of the sort illustrated here, and we want to try to prevent that, right? And so what this really means is that you should have a model that learns paradigmatic similarity. That is, it should assign high similarity to word pairs that occur in similar contexts, but not in the same sentence or are part of the same event, right? So you should assign high similarity to bird and gorilla, but not to bird and bamboo, for instance. And interestingly, the RNN does this very well. This was actually part of the reason that I chose the RNN, because word order is so important for performing this procedure that the RNN was an obvious choice, right? In contrast to many other models that don't even track word order explicitly or implicitly. Now, what else can we say about decaf? There's another really important constraint here. That is that decaf really is most effective at the word level, right? If we're interested in word learning, which we are, then what you have to do if you're going to support word learning in any useful way is to learn statistics about words. So let's illustrate this. For example, if our input is made a bit more complex, so the subject nouns are replaced with complex noun phrases, we're still interested in learning what gorilla means, right? You might use your distributional algorithm to identify that these chunks here, right, are distributionally similar, and you'd be correct. But that's not good enough, right? You have to sort of drill down to the word level, because if you're interested in the word gorilla and you've been working with chunks that are much bigger grain size, now there is sort of a question about, well, how exactly do you isolate shared semantic features of chunk level language units? There's a question about now, well, is it relevant that the cat bit this person yesterday, or is biting relevant to gorilla is yesterday, or red wings relevant to gorilla and is big and hungry, important for making these inferences, right? And so you'd be mixing and confounding lots of irrelevant semantic features. It's not to say that this would be impossible, but certainly would be much more effective if the model that we're going to be used to perform this task actually operated at least in part at the word level. What can we say about the RNN in this case, right? The recurrent neural network is actually quite bad at this, right? So it doesn't make any guarantees that it will identify word level phenomena. In fact, it's designed to learn sequences. And when it can, it will chunk words together into sequences and learn statistics at higher order grain sizes. That's what it does. And this follows from the objective that it is used to train the RNN, which is next word prediction. Essentially, when you're trying to minimize next word prediction error, you're going to exploit in any way that you can sequential statistics and try to chunk words that are predictable, and you chunk those together, right? So this is sort of an interesting scenario here, because on the one hand, the recurrent neural network is potentially really well suited to this task, performing decaf. It learns paradigmatic similarity extremely well. But on the other hand, it doesn't seem to really be effective at the word level, because it will tend to chunk word level statistics, right, into sequence level, chunk level statistics. So let's talk about the recurrent neural network a bit more detail, right? Given that this thesis is computational work, and we're trying to figure out what model and what aspects of a particular model are most useful performing decaf, let's take a look and see what we can find. In particular, I'm going to use the simple RNN, but of course, I don't think anything is particularly interesting about the simple RNN other than it's the most simplest form. In fact, I replicate all my analyses with much more sophisticated recurrent networks, such as the LSTM, and all my findings are relevant to a broad class of recurrent neural networks. Just want to remind the listener that the simple RNN is powerful and widely used in language literature, and is part of the reason why I've chosen it here as opposed to a more, domain-specific sort of expert system, right? The way it's trained is using the backpropagation of the next word prediction error. So in other words, it's learning is completely error-based and self-supervised. By predicting the next word in a sentence, the model notices important statistics, semantic, syntactic, or otherwise, that are basically useful for learning about the structure of a particular language. So the question now is, okay, we have a powerful model that can do lots of stuff. Can it learn semantic category knowledge, right, at the hidden layer? So we have to demonstrate that it learns semantic category knowledge, because this is, without that, it's basically worthless, right, for modeling decaf. Decaf rests on the crucial assumption that the model learns something about lexical semantic category knowledge here. So we're gonna use the following method. We're gonna train a simple recurrent neural network on a corpus of transcribed speech to children obtained from the Childish database. And I've compiled a custom corpus called the AO Childish corpus, which is an age-ordered version of American English speech to children. Right, so it's about 5 million words of American English. Remember, it includes dozens of children and caregivers, so by far it doesn't have, right, the ability to sort of tease apart individual differences. I've just clustered a bunch of speakers and listeners together here. There's about 3,000 transcripts. Each is a sort of different situation, and importantly is ordered by the age of the target child. So from the range of 1 to 6 years. Okay, so we have a corpus. We're going to train the simple RNN on this corpus, and during training, we're going to try to diagnose what the model has learned at the hidden layer. So we're going to obtain contextualized representations of 700 nouns. So all of this work is really mostly about nouns and learning semantic categories of nouns. I use 700 nouns for which humans have previously generated semantic category labels. So these are 700 nouns that not only occur frequently in the corpus, but for which we have human-generated data, so that we can compare the knowledge that the model has learned to the human-generated category labels. And importantly, I follow a standard procedure here, right? I'm just trying to sort of establish the feasibility of using the RNN for learning semantic category knowledge at the hidden layer. The way that this is done, right? The way that contextualized representations are computed is as such. For each of the 700 probe words, I obtained all probe final sequences in the corpus, AO Childish, right? So I go through the entire corpus, save all the sequences where gorilla is in the last position. These are all 7 item sequences, and then feed them all into the RNN. Here, the RNN is shown with a single hidden layer in green. Left to right are different discrete time steps. And I save the hidden layer state at the last time step and average all of those hidden states to produce one contextualized representation for each probe word. This is quite an involved procedure, and I'll argue soon that this is presumably not how children do it. This seems quite cognitively implausible, right? To store the entire corpus, feed it back in, and then do this for, God knows how many words. This doesn't seem a good way to perform decaf, especially for children in real time needing to, learn novel words. So this looks like the following. Imagine we have the black cat. We want to get the contextualized representation. We feed in each word at a time. And then at the hidden layer, at the last step, we basically collect the hidden layer activations. So importantly, what contextualized representations are is not just the representation of the word cat, but all of the previous context, right? All of the previous 7 items. And now, armed with these representations, we can compare these learned representations to the target semantic category structure, right? These are the human-generated labels, the human-generated category labels for each noun. And we're just trying to get a basic idea of how well the learned similarities correspond to, human knowledge. So a 2-dimensional representation of the learned similarities is shown here. We can already see in this figure, qualitatively, the RNN over the course of training on child-directed input learns to cluster words according to semantic category. This is really interesting and wonderful, in fact. So you've got quantitative concepts like days and months, times, numbers, right over here. You've got, animate categories, insect, bird, and mammal down here, artifact categories up here, tools and toys, and music instruments, kitchen items, and then food items cluster over here. But to quantitatively, evaluate this learned clustering or this learned similarity structure, we compare to human-generated category labels. There are 27 labels. Each probe word is assigned exactly 1 label. So a cup is a kitchen item, and a dog is a mammal, and so on. And we're just going to compare this. And the y-axis is the performance. So this is a measure of the semantic categorization performance, essentially, or the fit between the learned similarities and the human-generated labels. And in green, the performance is shown for the simple recurrent neural network. For each of these 27 categories, the model is well above chance, except for maybe times. And it's comparable to more sophisticated models like the LSTM shown in yellow and a machine learning model, Word2Vec, in black. So this just illustrates that using standard procedures, using contextualized representation at the hidden layer, these simple RNN and other recurrent methods learn rich, contextualized semantic category knowledge. So this is sort of the first step in demonstrating that potentially recurrent neural networks are useful as models of decaf. Remember, that is the distributional extension of category-associated features that children supposedly perform. Great, but there's much more to be said here, okay? So the RNN captures semantic category knowledge at the hidden layer. That is all fine and well. But is this knowledge learned in a way so that it can be readily extracted? And that is really the primary question of the thesis and most of the work that I've done in graduate school. So it must be readily available, right, by the child and to the child, right, if we're going to consider this knowledge to be involved in supporting the child's word learning, right? Remember, decaf. Let's think about this a bit more. So usually in the psychological sciences, especially in language acquisition, right, we build models that supposedly, hopefully explain aspects of behavior in some, hypothetical average child. We do this by generating model outputs and, evoking behavioral data from humans. And then comparing predictions. And if there's a good fit, we say that the model is a good model and can potentially explain aspects of, for example, language behavior in children. Now, the problem with the procedure and the methods that I've used and described just now is that there is this intermediate step where, in order to get the model to perform or to produce some output that can be compared with behavioral data, we use analytical or diagnostic methods that weren't really developed or aren't really plausibly considered, right? Things that children might actually do, right? This is just the experimenter swooping in using their entire knowledge and, computer and whatever the computer can do, like storing entire corpora and doing, fancy computations. The question is this a problem? I think it is. So the analytical methods that people tend to use to study the RNN aren't a good model of what children might do, right? So we really have to think about these analytical methods as part of the complete model, right? Because if they're used to generate outputs, then they are part of the model. And so we have to think carefully about these very sophisticated and memory-intensive procedures and analytical methods, right? And ultimately, the question now becomes a bit more technical, right? Because if we're interested in plausibility, right, and in building a sort of unified model where each step in that model is cognitively plausible, where we have to ask ourselves, okay, well, can the RNN acquire representations in a format that can be used to perform decaf, right? So we know in principle the knowledge is there. It's somewhere in the contextualized representations at the hidden layer. We know in principle the knowledge is there and it can do that. The question now is, can the RNN learn to represent this information in a format that can actually be used in a way that we think is plausible to be performed by children, right? So in particular, can we access this knowledge in the RNN without these sophisticated analytical methods? Remember, these analytical methods included accessing an entire corpus of 5 million words, right? And then for each probe word, collecting all sequences. You collect potentially thousands of sequences, feeding each separately into the recurrent network, right? All the while blocking the language processor. And then storing all the resulting hidden representations, and then averaging them and doing this all over again for a bunch of other words. To me, that sounds like a wonderful way to analyze the network, but totally implausible. And in terms of computational, tenability. So can we essentially get rid of this? And does the model still, can we access the model's knowledge in a way that doesn't require these sophisticated, memory-intensive analytical methods? If so, then we can say the RNN is a much, much more plausible contender, right, for explaining and simulating children's decaf, right? So can we essentially build a model that doesn't rely on this sophisticated procedure? So let's illustrate this a bit more visually, right? So we've been looking at knowledge in the processor, right? But I want to now take a look at the lexical representations. Why? So the matrix U is static. It's just a matrix that is always there, that you can just look up word representations in, right? U are the set of weights that connect the inputs, the hidden layer. And it would be wonderful, right, if the representations of interest, the word representations that the RNN learns, would just be in the weight matrix U, right? Instead of being sort of needing to be dynamically generated, right, in the processor, it would be wonderful if that same knowledge or an approximation of that knowledge existed statically at the weight matrix at the input layer U. And this is now where I'm going to start looking at lexical representations and looking for semantic category knowledge. And this is sort of the innovation, really, because people haven't looked at weight matrix U in recurrent architectures a lot, definitely not in the context of modeling decaf or learning lexical semantic representations. So the question is, does the knowledge that we know exists at the processor trickle down to lower levels of the network where it can be more readily accessed and where it's a much more plausible story, right, to tell about how children might access the knowledge that they learn. So let's introduce some theory and make this a bit more formal, right? So ideally, the RNN, right, would learn category knowledge at the input weights U. So let's illustrate this. So consider a two-dimensional weight matrix U. What we want here in this potentially semantic space is for words belonging to one category to cluster in one area of the space, and words belonging to another area to cluster in another area of the space. This is the ideal scenario. If that is the case, we can say that yes, semantic category knowledge has trickled down into the lower levels of the network where we can readily access it, and we're done. No need to perform sophisticated analytical, go through the entire corpus and so on, etc. This is the idealized scenario. And the question is, does this automatically emerge in recurrent neural network language models? It's unknown, right? So I call this property where the knowledge trickles down to the lower level is readily available, right, and makes sense. It's actually usable, and where the information, right, the topology, the geometric relations between words in that vector space can actually be used, right, to make inferences. I call this property of the system or the representations that that system has learned lexical atomicity. So how can lexical atomicity be achieved in the recurrent network? Okay, so imagine you're a recurrent neural network, you're getting sentences like the black dog and house jumps. Now, if you want to learn something about dog, like the semantic category of dog, the fact that it is an animal, that it is animate, and so on and so forth, there aren't really a lot of relations in that sentence that are diagnostic of this knowledge, right? In fact, I would argue that logically, there's only one such relation, and that is the relation between dog and jumps, because jumps tells you something about, what a dog is or can do, and sort of places it in sort of the category of things that are animate potentially, right? Not perfectly diagnostic, but it's sort of the best relation in the sentence, right? And if you're an atomic, if the goal, right, is to learn atomic relations and representations, you'd encode this relation discretely and more or less independently from all the other relations, because all the other relations don't really contribute additional information about semantic category membership. Sort of have to ignore them or learn to ignore them, right? So what you want to do is, over the course of processing, right, words, it's going from left to right, you want to activate the semantically relevant units, right? So units that are involved in predicting things like jumps or other animate verbs only at the step at which dog occurs and not at any of the subsequent or precedent steps, right? So you don't want to rely on context to activate the semantic properties, distributional semantic properties of dog, because those should be activated only when you see dog, that is, only through the representation of dog. So contrast this to a non-atomic system where dog does contribute, but only partially, right? So now this system is relying on context support, right? And in particular on neighboring words to help fully activate distributional semantic properties that are diagnostic of, for example, being in an animate category. So the word jumps, which is diagnostic, right, is now not only being predicted solely by the word dog, but is sort of helped by neighboring words. And I would say this is maladaptive for the purpose of modeling decaf, where we're interested in learning word level phenomena and helping children map, words onto onto semantic features, right? Because in such a system, dog only has partial information, right? And part of that information is sort of trapped in neighboring representations. So we don't want this knowledge to be trapped. We want it to be available at dog, where we can access it, right, without having to compute all the contexts, right, having to retrieve all these contexts in a corpus. We want the information to be just standalone and atomic, and we want that to be available at the input layer. So, I mean, there's nothing bad about necessarily a non-atomic organization. It's probably, really useful for things like reading and contextual processing in language. Lots of evidence showing that, this kind of sort of chunk level statistics is really useful in many situations. And I'm not arguing that atomicity is something that the entire language system should have. I'm just arguing for atomicity in the context of a particular tiny portion of the language system, which is used to perform decaf, right? And that system is actually, I would argue, very separate from meaning proper. And I'm definitely not against, and in fact, I'm absolutely for the idea that, meaning and concepts themselves are potentially highly contextualized or non-atomic, right? And that they can't be, chopped up into discrete units. Also remember that atomicity really refers to temporal credit assignment. So it's not about whether you can tease apart contexts from one another. It's really about teasing apart units in time, right? So don't mistake atomicity in this talk with maybe other types of atomicity that have been proposed in the literature. This kind of atomicity really is about temporal credit assignment and figuring out which discrete relations in sentences are most relevant for learning about semantic category membership and representing those independently of other intervening representations, relations. And to make this very clear, right, atomicity isn't necessarily that is a hard threshold that a system must have. Considering that the RNN is, after all, a statistical system, that would be rather naive to require that of the RNN. In fact, completely unrealistic. Instead, atomicity is more like a target that we aim for, right? And the closer you get, I would argue, the more useful that system is for performing decaf. So what is the prediction? So we've said that atomicity is important, right? What that really means is if you're gonna try to learn, distributional facts or statistics about words to support word learning, you actually want to learn at the word level and not just at the chunk level, right? Because those statistics are much less useful for decaf. So the prediction then for the recurrent neural network is that, the representations that it learns are not fully atomic. Nobody expects them to be fully atomic because, well, the semantic category membership knowledge is gonna be trapped at the hidden layer to some extent. But it may still be approximately atomic, right? And may therefore still be somewhat useful, right? The question is not whether or not representations are atomic. It's about how atomic, the degree to which atomicity is approximated, right? And that degree is the degree to which that model can be successful, right, at performing decaf. Let's test this prediction. So I've run a bunch of simulations, as I've already explained before. With the simple RNN, I've already shown the performance for semantic categorization using contextualized representations. On average, the performance here is well above chance. So above chance means it's above 0.5. A ceiling, you know, not clear what that ceiling level is, but 66 is pretty good. And 66 is the ceiling level for the performance for lexical representations, right? This is the maximum that you can get because the lexical representations inherit knowledge from contextual representations at the processor. And the question is just how good are the lexical representations? Are they complete garbage? How close do they get to this number, right? The closer they get to this number, the more atomic the knowledge is in the simple RNN, and the more likely or the better that model would be, right, for modeling decaf. So it should be less, but it's actually not much less, right? So extensive simulations, this is over many simulations, have shown that you know, you don't lose much information. Lots of information that is in the contextualized representations actually does trickle down into the lexical representations, right? Remember, where the knowledge is statically readily accessible, right? I've done this with the more sophisticated recurrent model, the LSTM, and I find a similar qualitative pattern. In fact, the LSTM, being more sophisticated, can extract much more semantic category knowledge at the hidden layer. So compare 66 to 69. But interestingly, the same amount of semantic category knowledge trickles down to the lower levels of the network. So there's really no advantage to using this more advanced model compared to the simple RNN when you're just looking at lexical representations. So, you know, you say a lot here about, okay, well, is the RNN now a good model of decaf or not? I would argue absolutely. You don't lose a lot of information, right, if you're accessing the lower levels of the network, right? I would say that, you know, you don't need these sophisticated analytical methods to extract that knowledge. All you need to do is go into the lower levels of the network and you get almost as good results. And again, that this has been, you know, gone through statistical analyses. These differences are highly significant and reliable. All right. So, you know, you might have a question about atomicity, right? It's a complicated concept. And I wanted to really not only show that you can get atomicity out of these networks, but also understand how that works and how we can improve upon these numbers, right? And so we have to sort of understand mechanistically how these networks work, and in order to, right, develop tools and strategies for promoting atomicity. I've done a number of, you know, extensive language simulations to formally test many predictions about how and under which conditions atomicity emerges in the RNN. For details, I'll have to refer you to the thesis, but briefly, I will say that these results show enormous differences in the kinds of properties that promote atomicity. So here I compare the balanced accuracy, the number that we've been talking about, for networks trained on 4 languages. Here I show the performance when using contextualized representations on different languages. And after a while, networks trained on each of these languages that differ widely, right? They all learn the semantic category structure. So it doesn't actually matter, right, what language you use if you're just looking at the contextualized representations, because all of that knowledge eventually is encoded in the contextualized representations. But it really matters when you look at, lexical representations of particular words. So this is the balanced accuracy of a particular set of words in these languages at the lexical representation, at the hidden weights. And you can see that although the contextualized representations in all these conditions, right, learn all of the semantic category knowledge that there is, the extent to which that occurs at the input weights differs enormously, right? So some networks here trained on a particular language called L just don't get it, right? And the knowledge in these networks is not at all available at a particular location in the network. It sort of dynamically emerges over the course of processing whole sequences, whole chunks, right? And so based on extensive simulations of this kind, I have developed a sort of language agnostic set of principles to answer the question, well, when does atomicity emerge, right? The answer is semantic property inheritance theory, or short spin theory. And the idea is quite simple. If you're interested in learning atomic lexical semantic representations in the RNN, and you're interested in a particular set of target words like 700 nouns, right, or whatever, these target words must observe the following properties in the training data. First, and not surprisingly, right, the target words in the training data must be succeeded by or followed by words that are informative about their semantic category membership. Unsurprising, right? Because that just says that there must be some grounds for clustering or grouping semantically similar words into the same cluster. But what is less intuitive is principle 2. And the idea is that while right contexts must be semantically informative, left context must not be. Right? So, you might think, oh, well, more information better. No, absolutely not. The recurrent neural network, at least ones that process information in one direction, they have a particular kind of sequence behavior where information that comes before you make a prediction is not incorporated in the same way than the information that is actually predicted. So there's a stark distinction between information that is predicted and information that is predictive. And so you actually want left contexts of target words to be totally uninformative so that the target word itself can stand out as a discrete standalone unit, and so that the network can learn that it is the sort of predictor. And if it is the predictor, then it can inherit all those semantic properties, right, and become atomic. So this is spin theory, right? And spin theory is wonderful because it makes language agnostic predictions about, when does atomicity emerge for any language, right? And makes predictions about or can guide us in thinking about how do we promote atomicity, right? And so in this last part of the talk, I want to talk about how do we promote atomicity, right? How can we do better? How can we get more semantic category knowledge trickled down into the lower levels of the network where it is statically and readily accessible by children? And one observation that has sparked this line of work is that, remember the counterbalancing requirement. This is the idea that left context should be semantically vacuous, right? Interestingly, in English, speech to children input to younger children actually really well approximates this counterbalancing requirement, much more than speech to older children, and definitely much more than speech to and among adults. So this is really interesting and really curious, and potentially suggests some some pedagogic value of the sort of lexical structure of input to young children in helping nouns become more atomically represented, right? This is speculative, but let's look at these results. So the prediction is that the RNN learns more atomic representations of nouns, right, when trained on age-ordered child-directed input, right? So input to younger children first, right? The idea is that if you train on input to younger children first, where nouns occur in less semantically informative left contexts, then those nouns become more atomic. And if you do that early on, you establish this nice atomicity bias, or you induce the sort of long-lasting learning dynamic that can sort of scaffold subsequent learning, and you get sort of these long-term benefits. So this is actually a quite simple intervention. It doesn't require adding any special machinery to the model or to the way that it learns, other than just organizing the input according to age order, and then actually making sure the model is incrementally trained on that ordered corpus. So the results are in alignment with predictions. So for the simple recurrent neural network in blue, I show the semantic categorization performance of models trained in age order, and they achieve long-lasting improvement. And compare that to performance in orange models trained in the reverse order. It's really interesting because there is no difference in information in these two conditions. It's just that the corpora are fed to the model in one order or in another, right? And it's just really interesting to see that the order matters, that one order can give you more information, even though we've actually just seen exactly the same corpus, right? But more importantly, it illustrates that you can get more atomic representations. So in blue, the y-axis is also a measure of atomicity, right? Because I'm using lexical representations, non-contextualized representations. So it shows that if you really focus first on inputs where nouns sort of stand out in sentences, that if you train on that kind of input first, you get long-lasting benefits for letting that semantic category knowledge about nouns actually then be trickling down into the lower levels, and it becomes more accessible. So this is really interesting, and shows also in addition just the benefit of using cognitively inspired interventions. Interventions of this sort really just say, let's look at how children learn, let's look at their language environment, and let's train our models as close as possible to mimic the situations in which children find themselves, right? So no additional machinery or modeling assumptions needed. And this is, I think, really fascinating work, and opens the door, right, to lots of potentially more cognitively plausible language learning simulations, and hopefully in the future people will respect the order of inputs much more, right, when training big models on language data, especially when modeling language acquisition. So I've called this the age order effect. And it's interesting not only because, right, of the idea that we can promote atomicity using developmentally friendly training, but because it suggests a potential deep similarity, right, between connectionist systems and humans, and the interaction between model and data, right? and the experiences that early on can have long-term consequences, right, for how a model processes information. So we can sort of return to the question about, do we need these analytical methods? Right? It would be nice if we didn't need these analytical methods to generate model output, and hope to convince you in this talk that they are, while useful, not necessary to get the RNN to produce useful output, right, at the input weights. So at the input weights, we don't need analytical methods to access that information. It's readily available where a child could use it. But are we there yet? Well, there's still a difference here, right? So overall contextualized representations still get you more information. So this is the difference between the red bar here and the gray bar. Whether you find this important or not probably depends on personal preferences. I certainly think that you can go a long way without needing to access and compute contextualized representations. But yes, this does illustrate that there is still some way to go, right? If we're going to close this gap, I would suggest building in or using additional tricks, right? Just like age ordering, I consider to be one of many tricks that modelers can use, and hopefully will in the future look more to the language environment of children and see what else can we learn there to improve how we train our models. Let's do some concluding remarks. There's some limitations. One severe limitation that needs to be worked on in the future is the RNN in my work already comes with pre-segmented units. So I've used a variety of segmentation strategies, right, that essentially mean that the RNN already has available as a discrete vocabulary, right, that typically correspond to word-like units, dog and cat. But of course, children have to learn to segment, and none of this is really captured or being done in my model, right? So it'll be interesting to build a model that doesn't just segment first and then learn meaning later, but does this simultaneously, and presumably through that interaction, you might even get better results or exponentially worse results. This is extremely difficult to do, and this is an ongoing work in the speech recognition and language learning literature. Some preliminary work of this sort in the lab, not necessarily using speech, but using different segmentation strategies, suggested that there are main effects of segmentation strategies, so that, for example, more linguistically informed segmentation strategies like morphological parsing can give you much better semantic categorization performance, but actually it doesn't change the age order effect, interestingly. So the age order effect seems to be really robust against the segmentation strategy. If you use less linguistically informed segmentation strategies and you use, for example, byte-bear encoding, which produces subword tokens that are more popular in the machine learning literature, interestingly, you get worse overall performance. So semantic categorization is reduced. So there's another whole sort of literature on the importance of chunk level knowledge, right? So I have talked at length about the importance of word level, lexical atomicity. How does that square with the need for chunk level knowledge? And in particular, I have in mind work by Morten Christensen on the really interesting now or never bottleneck theory, which claims that chunk level knowledge is important, crucial for language learning. Things like grammar and just reducing the amount of memory during online language processing. But it's not exactly that these two ideas are competing. In fact, I would argue that a language learner should keep track of both kinds of statistics, both kinds of grain sizes, so that they should both store chunk level units as well as more lexically atomic units, right? And so the really interesting question there is to, try to figure out what is the interaction between chunk level units in language and the word level units. Are they stored separate systems, and how do they talk to each other, and so on. Finally, none of this work presented has tested the ideas in actual children or in any form in behavioral work. So it would be wonderful and lovely if future work would test some of these ideas using, for example, eye tracking or the visual word paradigm, artificial grammar learning studies, anything to test the idea whether recurrent neural networks are actually a good fit, right, to learning distributional semantic properties of words. And lastly, actually, I haven't really modeled the full scope of decaf, right? Remember that involves not just learning about and acquiring lexicosemantic representations, but also using those to extend word meanings. And so that would require, a theory of word meaning and corpus of semantic features and the corpus of, words and when they are required and so on. And so that'll be an interesting future line of research that would require going much beyond the recurrent network and let that model interface with a much bigger system that also hooks into right, so more of conceptual word meaning and semantic memory systems. So finally, I'm going to conclude the simple RNN is a powerful model for learning arbitrary dependencies in natural language data and learns rich contextualized semantic knowledge at the hidden layer. But distribution semantic information is often trapped at the hidden layer. And this limits the atomicity of learned representations, which we need to perform decaf, the distributional extension of category associated features. And interestingly, one really simple way to promote atomicity is to just train the RNN on input that respects the developmental trajectory of children's language environments. And so my hope is that interventions of this sort, using cognitively, developmentally inspired ideas and findings in the literature to improve how we use connection systems, can eventually, hopefully one day, arrive at the full repertoire of language in children. And with that, I want to thank John Willits, my PhD advisor, my doctoral committee that includes Cynthia Fisher, John Hamel, Gary Dell, and Aaron Benjamin. And also lastly, members at the UIUC Learning and Language Lab.